So 6.6, modeling with trig functions. Okay, so we're going to do an overview of the trig functions, what we're going to see in word problems, and then we're going to go ahead and apply these concepts to word problems, okay? So maximum value, we already know the equation for the, like if given an equation, the equation for maximum value is equation of axis, plus amplitude, and then the minimum value, I reverse these again, equation of axis minus the amplitude. Okay, these two are going to be like if we're given like either the information, info, or equation. You can definitely like pick those out. Okay, period is 2 pi by k. As a recall, this k value straight from the equation. Straight from the equation. Okay, amplitude and equation of axis go hand in hand with the max and min. So if you need the amplitude, if you have information on the max and min, so this is going to just come from information from the word problem. Okay, amplitude is max minus min divided by 2. And then equation of axis is max plus min divided by 2. Okay, and the critical interval is going to be whatever your period is divided by 4. So just remember there are 4 sections in sinusoidal graphs between the points. Okay, so just as a quick example, if we had like the cos graph, if you think about like the sections, this would be like one section. This would be another section. Change color. This would be maybe another section, section 3. These are not in order, by the way. And then this would be section 4, right? So there's 4 sections that are divided by these like 5 critical points. And that's why we do the critical interval divided by 4. Okay. So first, sketch the curve that takes into account the A and C values. So a lot of times you'll see approaches where, like we've done mapping notation, but you'll see approaches where they plot the original sine or cosine function, and then they apply all the stretches, compressions, and reflections first. Okay, so that obviously is like your A and your K values that they're plotting first. What we did is like we did mapping, and then we focused on the X and the Y axis, which is essentially the A and the K, right? Like how the vertical and the horizontal axes change the scale depending on how we're going to graph this. But when we do word problems, this is definitely like a key component of it. Okay. And then after that, what you want to do is you want to do the shifts. So the H, obviously that's like left-right shift. And then the C is the up-down shift. And then you're going to take into account everything. Okay, depending on the style of question, I'm going to approach it differently. Okay, so let's talk about the algorithm for sketching sinusoidal functions in word problems. Okay, so up until now we've used mapping. Now we're just going to simply pattern. And you'll see how easy it is to pattern. And we've already talked about like the max-min equation of axis and doing like the dotted line, and all 5 critical points are going to lie on one of those. So you're already like 10 steps ahead right now. Okay. So first what we're going to do is we're going to create the scale on the x-axis using critical intervals. Then we're going to create the scale on the y-axis using our max-min and equation of axis values. I have to change this. No, I'm sorry. Then what we're going to do is we're going to mark our max-min and equation of axis values on the y-axis, and then we're going to make those dotted horizontal lines across that we've already seen. Okay? And at that point, what we want to do is we're going to find our starting point from the phase shift, and then we're going to pattern. Okay, so our patterning is going to look like this. So the 5 critical points for sine starts on the equation of axis, goes up to a max, back down to the equation of axis, down to a min, back up to the equation of axis. And the reflection of sine is opposite that. So instead of going up first, the reflection of sine is going to go down first. Okay? Now, cosine x. Start at a max, go down to the equation of axis, down to a min. So that's double down. Up to the equation of axis, up to a max. And the reflection of cos is going to be opposite. Min, equation of axis, max, equation of axis, min. Okay, and we're just going to pattern. Okay, example 1, the height above average sea level. So by the way, average sea level, we would call this height of 0. Okay, in meters of the tides at the Bay of Fundy after T hours can be modeled by the sine function below. So here's our sine function. This question is already easy because this is what we've been dealing with so far. They give us a function, cool, we just have to read the function. So A, the amplitude and its real life meaning. So what is the amplitude? Well, amplitude is obviously 6, right? So 6 meters. And what is the meaning? The water level goes 6 meters above and 6 meters below sea level. Again, sea level is like universally known as like the height equals 0. Okay, the equation of axis and its real life meaning. So the equation of axis in this is actually 8. So maybe like for the scope of this question, they're interpreting the sea level as 8, like the resting level. Yeah, and that's exactly what it is. Because if you think about the curve, right? So if you start at 8 and then you go up, down, and back up to 8, right? You're talking about like that like resting, like let's go like the resting sea level is 8 meters high. Okay, so again, universally, we do h equals 0. I guess for this, we had to read a little bit deeper into the equation, and like the rest, like the actual sea level is 8 meters. The max and min height of the tide, okay? So max is going to be equation of axis plus the amplitude, which is 8 plus 6, which is 14. Min, same thing, but minus the amplitude, 8 minus 6, which is 2. Okay, so 14 meters and 2 meters. Okay, and the period in its real life meaning. So period is 2 pi by k. So we're going to go 2 pi by, our k value is pi by 6. I'll write it right here. That's our k value. K pi by 6. If you're not comfortable with a fraction over a fraction, take it to the side of your paper. I'm going to rewrite this as 2 pi divided by pi by 6. And we can't divide fractions. So let's go 2 pi times 6 over pi. And we cancel out the pi's and we get 12. So what is the real meaning of 12? It takes 12 hours, and this is like a real life thing, for a tide to cycle through. Let's go from high tide to high tide. Right? Because we start at high tide, we go to low tide, and then back up to high tide. E, when the critical intervals occur. So a critical interval is going to take our period, which is 12 hours, and divide it by 4. So every 3 hours, we're going to have a critical interval. And then F is kind of like a one-off. What's the height of the tide at 14 hours, right? We can just do H at 14 equals 6 sine pi by 6, 14 minus 2 plus 8. Okay. And how I would calculate this, I would leave 6 sine, and then I would do, well, what's 14 minus 2? It's 12. So this is essentially 12. So 12 over 6 is 2. I get 2 pi, and then plus 8. Sine of 2 pi, well, we know that value because you can just draw sine. Sine of 2 pi is 0. So this entire sine 2 pi is going to be 0. 6 times 0 is 0. It's 8. So at 2 o'clock in the afternoon, or 1400 hours, it's going to be 8 meters high. Okay, so G, graph this function. Okay, so going back up here, we're talking about the height in meters after T hours. Okay, so this is going to be T in hours. This is going to be height in meters. Okay, and then we can say like Bay of Fundy tide. Nice label. Okay, so we're going to mark the X and the Y axes. So we have a shift right 2. So we have a shift right 2. So this is where we're going to start. And our critical interval is 3 hours. So 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. Okay? And then we're going to take the max min and equation of axis. Okay? So 14, 2, and 8. So 14's here. Let's do max. Okay? 8 is here and 2 is here. So let's draw those horizontal dotted lines. Okay, so I put this from the algorithm down here. All 5 critical points should occur on a max, min, or equation of axis. So now that we set up our graph, we can just pattern. So we do have a sine x, and we're going to start at 2. Sine starts on the equation of axis, goes to a maximum. So 1 critical interval later, which is 3. I'm going to do this with a brighter color. Let's go red. There we go. Okay, so 3 hours later, we're at a max. 1, 2, 3. Back down to the equation of axis. 3 hours later, we're at a min. Oh, sorry, equation of axis. 3 hours later, we're at a min. 3 hours later, we're back at an equation of axis. Okay, at 17 hours, we're back at a maximum. Okay, 3 hours later, we're back at equation of axis. 3 hours later, we're back at a minimum. And let me see, H at T. Let's just call this H at T. Example 2, the graph below models a Ferris wheel ride at an amusement park. Okay, find a sine, so not cosine, but specifically sine expression for the height in meters as a function of time in seconds. And use the chart below to help guide your answer. Okay, so I'm going to find the maximum. Max is 15.5. Oh, I can write it right here. Okay, and then I'm going to find the minimum, which is 1.5. Okay, and you can see that. You just read that straight off the graph. Now, period. The period is going to be 1 full rotation. So I suggest that you don't do it from the equation of axis. I usually do it from like min to min or max to max. I like this question because the minimum occurs as like your first point. So the minimum occurs at 0. And by the time you get back up to a maximum and then back down to a minimum, it's been 16 seconds. So the period is 16 seconds. I guess for max and min, we can put meters on there. Okay. And the K value is going to be 2 pi divided by P. Okay, 2 pi divided by 16 is pi by 8. Okay, amplitude, VU. Okay, I'm not going to read the amplitude right off the graph. Sometimes with the equation of axis, like to eyeball it is a little difficult. So for the amplitude, I'm going to go ahead and do 15.5 minus 1.5 divided by 2. 15, 14. So I get 14 divided by 2. The amplitude is 7 meters. So the hump up and the hump down will be 7. And then the equation of axis is going to be the 15.5 plus 1.5 divided by 2. If you think about the equation of axis, it's actually the average. So you're looking at like the middle point, 15, 16, 17. So I get 17 divided by 2. So I get 9.5, 8.5. Okay, so 8.5 would be here. I mean, that would have been very difficult to identify, but that's okay. We found it algebraically. And then the humps up to the max or down to the min would be 7 meters. Okay. So the height at time t is going to be, I'm going to show you guys a trick. See how we start at a minimum? Sometimes we're able to use like the negative cosine function, but now actually thinking about it, this is a sine function. So we have to start on the equation of axis. So our equation of axis is here. Our starting position would be 4 for sine, because sine starts on the equation of axis and goes up. So let's work with that. Okay, so the amplitude is 7. We're going to have sine, the K value, which is pi by 8, x minus 4, because we're going to the right 4 units, and then plus the equation of axis, which is 8.5. So this is our equation. Okay, use the equation to determine algebraically the height of the Ferris wheel after this many seconds. So we're finding the height at 14.5. So 7 sine pi by 8, bracket 14.5 minus 4 plus 8.5. So my recommendation is to do this first. So 14.5 minus 4, this is going to give you 10.5. I am going to multiply it by 3.14 divided by 8. We are going to get a decimal, and that's not going to change, okay? Because this doesn't nicely cancel with the pi by 8, like the 10.5, and because it's not nicely one of the special triangles, we know we're going to get a radian measurement that has a decimal in it. Okay, so sine of 4.12125 is going to be 7 times negative 0.830306 plus 8.5. Okay, I'm just going to leave that in my calculator. I get negative 5.812 plus 8.5. Sorry, 2.68785. Okay, so we can say, therefore, the height of the, and if you put FW, I'm okay with that, Ferris wheel at 14.5 seconds is let's round 7 meters.